I wanted to see what it would be like to build a chatbot web app similar to ChatGPT using Rust on the front end, Rust on the back end, and only free and open source language models, all while using no specialized hardware. I wanted to be able to run everything on my personal laptop. That said, let's take a step back for a second. Python is generally considered the language for machine learning, which includes language models. JavaScript and TypeScript are usually the go-to languages for front-end development. And at the moment, OpenAI's ChatGPT is the go-to for a high-performance conversational language model. So conventional wisdom might lead you to think that this could be a big undertaking. It actually turned out to be a lot easier than I thought it would be, and I'm going to walk you through exactly how to do it step by step. This is what we're going to build. Obviously, it doesn't have all the functionality of ChatGPT, but it's got the core functionality. We can see it gives some pretty accurate responses, even for some somewhat open-ended questions. And it does so pretty quickly, at least on my personal laptop. There are three main open source components that we're going to use to build this thing. We'll be using a free open source language model as sort of the nucleus of the whole project. The performance of open source language models is actually improving very rapidly, as is their memory efficiency, which means it's becoming increasingly feasible to use them on personal computer hardware, which will save you from needing to buy ridiculously expensive GPUs or provision crazy expensive AWS instances. The model we'll be using in this video is called Wizard-Vicuna, and we'll be using the 7 billion parameter version, which I found to have a pretty good balance of performance and accuracy. When we download this model, which is actually a 7 GB file, it's basically just a set of weights that represents a transformer neural network architecture, so we can't do anything with it by itself. We need a Rust crate that can load it and use those weights to generate responses to our prompts. The Rust ecosystem is fortunate to have a crate called Rustformers/LLM that does just this. It supports loading several different flavors of Transformer, Llama, Bloom, GPT-2, GPT-J, and so on. Each of these broad varieties of language model have quite a few sub-varieties, and in our case, the Wizard-Vicuna model is of the Llama variety. And then we have Leptos, which is a Rust crate for full-stack web development. Leptos has really been shaking up the Rust web app development scene lately. First of all, its front-end component is more performant than most reactive JavaScript frameworks. A reactive front-end framework called Solid.js is widely considered to be one of the most performant reactive frameworks, and it also happens to be the framework that Leptos' reactive API takes the most inspiration from. And the author of Solid.js, Ryan Carniato, even acknowledged the success of Leptos in this tweet, showing that it's more performant than the majority of the popular JavaScript reactive front-end frameworks. Okay, now let's get into building this thing. There are a few quick things that we need to do to set up the project. First, let's make sure we have the WebAssembly target installed, because we'll need that for building the front-end component. So we'll do rust up target add wasm32 unknown known. We'll also need to install two tools with cargo. One is trunk and another is cargo leptos. So we'll do cargo install trunk. You can see I already have them. A trunk is basically a tool for local hosting while you're doing web development and has hot reloading. So when you change something on the front end, it'll automatically refresh your browser, so on and so forth. And then cargo leptos is a tool that's specific to Leptos, and it supports hot reloading in the full stack. So if you make a change to the back end, it'll do a hot reload and incorporate those changes into your running server, basically. Now that we have all those tools installed, we'll actually create the project from a template. So we'll do cargo leptos new, and then there's a GitHub repository with this template. It's at leptos-rs/start, and it'll prompt us for the project name. We'll call it Rusty Llama. Now we can cd into the directory, and we can actually do cargo leptos watch, and we should get a basic Leptos web app. It's going to build, so when we do build cargo leptos watch, it's actually going to build both the front end and the back end, which is nice. Okay, so now we get the simple counter app. So this is our project here, and we can go into source app.rs, check out the contents of this h1 tag, and instead of welcome to Leptos, we can do welcome to Rusty Llama, save it, and we get hot reloading there. I didn't restart cargo leptos watch, and I didn't refresh the page in the browser. It just automatically updated for us. So quick overview of the project layout. Both our front end and our back end are both in this Rust workspace, which is really nice because you can build them in conjunction. In the source directory, we can see app.rs is kind of the entry point for our front end, and main.rs is kind of the entry point for our back end. So if you're familiar with the Actix web framework in Rust, the main.rs will look very familiar to you because Leptos uses either Actix or Axum under the hood for the backend component. So the way this looks is going to be very similar to what it would look like if you're using those frameworks out of the box. And then on the front end, if you're familiar with Solid.js or React, this is going to look very familiar to you as well, because we have this concept of a function that represents a component on the page, and each component can accept properties through its arguments, and it can have some state that it manages and potentially passes to children components. So it's very similar to React and Solid in that sense. And if you're familiar with Solid, you'll be familiar with create signal, same name and functionality as it would be in Solid.js. You will notice throughout the project there's these CFG macros, and they refer to features like SSR and CSR. Basically, SSR is a feature that's turned on when the server side of the project is built. Functions that are annotated with the CFG feature equals SSR macro are only going to be built when the backend is built. And conversely, ones that are annotated with CFG CSR are only going to be built on the front end. And that's very useful because it helps manage our dependencies. There's lots of Rust crates that can't actually be built in WebAssembly. So that helps kind of prune the dependency graph depending on whether we're building for the front end or the back end. For example, we don't want to build the Actix framework for the front end component of this project. That wouldn't make sense. And if you look in cargo.toml, we can see the example I just gave of Actix. Actix Web is listed as an optional dependency. And for CSR, Actix Web is not included in the set of features for the CSR feature, but in SSR it is. We have dep::Actix Web. So that's how we dictate that certain crates are only built when the backend component's built and not for the front-end component. One other thing to note is that I'm going to be using Tailwind CSS for this project, and there's plenty of resources online for Tailwind CSS in general. And there's also an example of integrating Tailwind into a Leptos project in one of the examples in the Leptos repository. So if you have questions about the Tailwind CSS integration, you can either check out this example on the Leptos GitHub repository, or you can look at the code for this project, which I'll have a link to in the description. If you have any questions specifically about that, feel free to ask in the comments as well, but I'm not going to cover that integration or anything about really Tailwind CSS classes in this video. I'm going to try to focus on the Rust aspect of things. Okay, so how's our app going to be laid out? The front end is going to be comprised of three main components. One is the chat area, which is the place where the conversation is being shown. And the second is called type area, which is where the user will type their prompt. And the third is our app component. That's kind of the root of everything, which will contain both the chat area and the type area. So by default, the default project has this app component with a router in it and a homepage component that is pointed to in one of the routes. We won't need any of that. So we can actually go ahead and delete the homepage component, and we can also delete this router because we're not going to need that either. And of course, this is going to be called Rusty Llama. And we're going to have, again, two components, chat area and type area. I know, naming things is not really my forte. Obviously, we're going to have more, we're going to fill in some of the logic here, and then also we're going to pass some things eventually to both chat area and type area, but this is kind of the overview of what it's going to look like. And before we start implementing any of the logic, we should probably establish a model, and we'll need a model to represent a conversation that's happening between the user and the language model. So we'll create a conversation struct, and that's going to be in a new module called model. We'll create conversation.rs, and yes, we want to create the directory. And then in this directory, we'll also create mod.rs, which will include conversation. And then we'll refer to this in lib.rs to add it to the source tree that the compiler is going to be aware of. Before we create the conversation struct, we'll need a struct to represent a message. And a message has two components, really. We need to be able to distinguish between messages from the language model and from the user. So our message struct will have two fields, one for the actual text of the message and another, which is a Boolean that represents whether it was from the user or not. And from there, we can create our conversation. And the conversation is just going to be a vector of messages. We will need to serialize and deserialize these things because they get passed back and forth between the client and the server. So for that, we'll need SERDI, which is for serialization and deserialization. And we'll need to annotate these with a derive macro. And we'll add that to both conversation and message. And we do need to add SERDI to the project, which we haven't done yet. So we'll do cargo add SERDI, and we want the derive feature. So -f derive. Check to make sure that works. Yep, that looks good. No more errors there. We'll also want a convenience method so that we can create a conversation easily. It'd be nice to be able to create a conversation without having to specify an empty vector every time. So we'll just create an implementation block for conversation and just create a new function. And that should be it for the model. Again, this user Boolean will be true for cases where the message came from the user. So for what year did it happen and what did Apollo 11 accomplish, the user field for those messages would be true. Now that we have our model squared away, we can go ahead and start creating some of the logic for this kind of root app component. The first thing we'll do is create a signal. So we saw a signal briefly earlier in the example project, but we're going to create a signal for a conversation. And when we create a signal, it's going to return a tuple with the first value of the tuple being a read signal and the second value of the tuple being a write signal. So those work how they sound. Basically, if you want to consume the value of the signal, you would use the first one. If you want to update the value of the signal, you'd use the second one to do that. So one create signal call, and we get two things back, one for reading, one for writing. Of course, we need to include conversation struct here. So we'll do that. So now if we wanted to, we could actually go ahead and do conversation.get and then print out whatever part of the conversation we want in the view template. The page that comes from that view template would be re-rendered automatically when somebody else updates that signal. So that's the reactive nature of Leptos, but we're not going to read from the conversation right there. We're actually going to wind up passing it to chat area, but we'll see that in a minute. The next thing we'll create is something called an action. And this entire app kind of revolves around the user entering some text and clicking that submit button. And when the user clicks that submit button, it's going to kick off a sequence of events. First, we're going to add the user's new prompt to the conversation so it's visible in this chat area. And then the second thing is we're going to send that new prompt to the server, where the server will use the language model to do some inference on that new prompt. And then the server is going to send back the new inference, and our front end needs to wait for that new inference to come back. When it does come back, we need to add that to the conversation. On that message, obviously the user flag is going to be false. And then at that point, we're done. We've added the user's new prompt and we've added the response from the language model. And the best abstraction Leptos provides for facilitating that sequence of events is something called an action. We're going to create an action called send, and we do so using create action. And create action takes the scope, which we have to pass everywhere in Leptos. That may not be the case when you're watching this. I know there's an effort to get rid of the need to pass the scope around everywhere and kind of do it implicitly. But for now, in this video, I'm going to be passing the scope around everywhere. So if when you're watching this, if in the Leptos examples, you don't see the scope being passed everywhere, they probably got rid of it. So just ignore the CX everywhere. It's like the first argument for function components and creating signals and creating actions, so on and so forth. But the second argument to create action is a closure that takes the input to the signal, which the type area is going to give later. You'll see that in a minute. For what you need to know now, the action is going to take the new message that the user typed in, which is a reference to a string. And once we get that string that the user entered, we're going to create a new message struct from that string. We need to write to the conversation because the conversation is being updated. So we're going to grab that set conversation signal. The update method takes a closure, which takes one parameter, which is the existing value of the conversation. So we can go ahead and modify that. So grab the messages and we'll push the new message onto the vector. And then somehow, which we'll see in a minute, we need to send that conversation to the server and take an action when we get a response back. We're going to do something here to send things off to the server. Oh, we also need to include this message struct. We haven't implemented these chat area or type area components yet, but for our type area, we're going to give it the send action. So when the user clicks submit, the type area component can actually call .dispatch to kind of initiate the action, passing it the contents of that input field that the user typed in. We haven't implemented the chat area either yet, but ultimately we're going to send that or pass that the conversation signal. So it can put the conversation in its reactive view, and that'll get automatically re-rendered every time the conversation's updated. Okay, now I'm really excited about this next part because it's actually one of my favorite features of Leptos. We're going to go ahead and implement the backend API that we're going to want to call every time this send action fires. We're going to create a file called api.rs, and that'll be a file that holds all of our server-side functions. We are going to need to add that into the source tree in lib.rs. We're going to do pub/mod API, so the compiler and LSP are aware of it. And we're going to create this async function. Async function converse. It's going to take a scope and a conversation, returning a result, which in the successful case is a string, and in the error case is a server function error. And I'm going to annotate this function with this server macro. So we're going to do server, we're going to give it a name, which is converse, and a path, which we'll do /API. For our use statements at the top, you need to import conversation. This function allows us to create a server-side API with logic that only runs on the server, but it also automatically creates a function, another function with the same name that can be invoked on the client side to automatically make an HTTP request to that corresponding backend API. So in the client, you don't actually need to manually create an HTTP request, specify the URL for the API, and do all that stuff. All that kind of integration is done for you. All you need to do is specify the stuff that you want to send from the client to the server in the parameters, and then specify the thing that you want to return to the client in the result. And in our case, that's a string. So this is really cool. This is one of my favorite features of Leptos. I look for similar functionality in kind of the JavaScript ecosystem, and I didn't find anything quite like this. They do make things pretty simple in Next.js and SvelteKit, for example, but I couldn't find anything quite like this. Let me know in the comments if I missed it. Maybe this pattern exists somewhere in the JavaScript ecosystem too. I couldn't find it, but yeah, it makes things really nice and it allows you to iterate very quickly. On the server side, we need to take this conversation and perform some inference and then return the result back to the client. We're going to paste in some imports here that we're going to need. And now I guess would be a good time to add the LLM crate to the project. Go to the TOML file. I'm actually going to paste this in instead of doing cargo add because I want to depend directly on the GitHub repository for the LLM project. At the time of this video, it's kind of under rapid development and things are changing. I wanted to use the latest version. If you want to rely on a stable version, I think 0.2 is the version that they're working toward at the time of making this video. So if 0.2 is a release when you're watching this, you might be able to change this Git reference to version equals 0.2, and ideally all the APIs will be the same as what you see in this video, but not guaranteed. For now, I'm just going to point directly to the repository. Now that we have the LLM crate added as a dependency, we need to add it to the SSR feature. So it's only loaded when we're on the server side. If you're familiar with the Actix web framework, there's a concept called extractors that allows you to get at various pieces of the HTTP request, but they also allow you to share one common piece of data across all of your server-side logic. And that's useful because the Actix web framework is the one that's invoking your server-side logic. So you can't really explicitly specify what you want to pass to these kind of server functions. So to get around that, we create what's called app data in the Actix world. And then in our handler functions, which is what converse is, we can actually extract that piece of data, which in this case will be our model. So we're going to do model equals extract. And this looks a little different than it would if you were doing it directly with Actix Web, but similar concept. So data is going to be the Actix data wrapper that contains our model. And llama is actually the LLM struct that contains our loaded model. And we're going to do data.into_inner, which will extract the contents of that data wrapper. Don't worry if that's confusing. It'll become clear as we get further. And this is an async function, so we need to do await, and we're going to wrap the results. And then we're going to start to set the stage for what we're going to pass the model to create inference. Ultimately, this is the format of what we're going to feed to the language model to get our inference. We're going to set the stage where the first line is going to be a chat between a human and an assistant to give context. And then we're going to have kind of a tag for each part of the conversation. For assistant, we're going to prefix that line with 3 hashes and the word assistant, and then whatever the assistant says. The assistant is the language model in this context. And then human is going to represent what the user said. And we're going to have this back and forth between the assistant and the human. Every time we feed the language model, the prompt is always going to end with assistant and this blank kind of line of text. Language models in general, they take text as input and they spit out some text as output. And in this case, the model is trying to predict what comes next in this sequence of characters. And so it's gonna internally, it's gonna understand that this is a conversation and the conversation has cut off when it was the assistant's turn to speak. So it's going to output what it predicts that the assistant is going to say given this conversation. So every time we feed something to the language model, it's going to be in this kind of format. So we'll start building that out. This is what's going to prefix the prompt every time we do an inference. At this point, we need to append whatever previous messages are in the conversation that the user was having. So we took a conversation as a parameter to this converse function, and so now we need to iterate over it. We have this kind of pre-built-in history right here, which is going to be there regardless of what the user and the AI have been talking about. And then we're going to append everything that the user and the language model have explicitly said in this particular conversation. So this part will be unique to this particular conversation. But we're going to append those messages to history in a format similar to what you see up here, with a line break between each message. We're going to set up 2 strings on a random number generator that we're going to use in a minute. And then we're going to call start session on the model. Again, in like a production scenario where you're really optimizing for efficiency, you'd probably save off the session on the back end and you wouldn't start it every time the user makes or enters a new prompt. But in our case, we're going to just start the session every time they make a request. Now that we have the session, we're going to do session.infer, and we're going to pass a bunch of stuff to it. The model, random number generator, an inference request, which includes the prompt as well as some parameters. So this is the actual prompt we're going to wind up feeding into the model. Again, we have the persona, which is kind of the context of the conversation, the history, which includes that prefabricated history with the actual history of this particular conversation appended onto it. And then the last line is going to be the character name, which is the language model's name. So that'll kind of clue the language model into knowing that it needs to predict what's going to be said next in the conversation. And then we have some parameters, and we're just going to use the defaults here. I haven't personally played with any of the inference parameters yet. I seem to get pretty good results without kind of tuning anything. If you're having a specific problem and you want to try some tuning before you resort to using a different model, this might be something to play with. And then these are kind of two other sort of configuration parameters, playback previous tokens and maximum token count. We don't want to limit the token count and we don't want the previous tokens. So we're going to set that to false. So that does it for the inference request. And then this is an output request. I honestly haven't played with this. I'm not sure exactly what it does. And the last parameter to this infer method is an inference callback function, which we need to implement. And we want to panic if something goes wrong here. This is probably the most complicated part of this whole program. So if you can get through this, you can get through anything. We also need to add this RAND crate to our project for only the server side. We'll do RAND with optional equals true, so it doesn't get built when the CSR feature is enabled. And then again, in SSR, we'll add a new element here, RAND : dep : RAND. So it gets built when the SSR feature is enabled. We do need to implement this inference callback function. So I'm actually going to copy and paste that in. I'm not going to go too into detail about what it does. What you need to know essentially is that this inference function needs to know when it should stop getting new tokens from the language model inference process. The inference will basically keep going and going until you tell it to stop in this callback function that you pass to the infer method. In this case, we want the inference to stop whenever the model outputs the human character name, if that makes sense. So I've copied and pasted in this inference callback function, and we can see it's only compiled into the server-side binary, and it's going to take a stop sequence, a buffer, and an output string. Yeah, I'm going to skirt over what this logic actually does. Long story short is it's going to look for the username, which in this case is human. When the inference outputs a prompt for human, so let's look at what's happening. So assistant's going to have some response. It's Washington, DC, and then the inference is going to output human : At that point, we detected that the inference has output the prompt for the user, and so we want to tell the inference to stop. If left to its own devices and we don't tell the inference to stop, the model will happily start inferring what the human's going to say. The humans asked for 2 capitals, so at this point, it might assume that the human wants to ask for another, the capital of another country. What about Canada? And it'll just keep going on and basically have a conversation with itself. We don't want that, so that's what the inference callback function is designed to do. It's designed to detect that the set of tokens that represents kind of the user's turn to talk and then stop the inference when that happens. We're adding to outstir, which is the response that we're going to send back to the client. And then from the inference callback function, we're actually returning OK halt or OK continue. That's what tells the LLM crate whether to continue with the inference or not. I made an awful mistake putting a semicolon on this line. Doing so means this closure that we pass to extract doesn't actually return anything. So model becomes like of type nothing. So I'm going to remove this semicolon, and that should fix a lot of these compiler errors here. And this parameters field actually doesn't need to be wrapped in an optional. So remove that. In a previous version of the API, it needed to be wrapped in an optional. We're never appending cur line to history. History.pushStir cur line. Oh my gosh, I put this in earlier to make some errors go away and I forgot to remove it. All we actually should have to do is do OK res here. So this res is being appended to in this inference callback. If we go down here, res becomes outstir, which is what we're going to wind up sending back to the client. One thing you definitely want to note about this function is that it is a public API, so there's no authentication or authorization by default on this thing. So that's something to be aware of. I'm not going to cover any auth in this video, that's kind of out of the scope, but if you're going to productionize this, make sure you secure these APIs somehow. The next part we need to work on is loading the model. And in this function, we assume the model has already been loaded when the server, the ActixWeb backend was started and placed into this ActixWeb data wrapper. So now we're going to do that. I mentioned the entry point for the ActixWeb backend is in main.rs. So we'll go in there and we're actually going to write a function for loading that language model. And again, it's only going to be compiled on the server side. So we're going to do a CFG if for that. We're going to have some imports and we're going to call this function get language model. And it's going to return a llama struct, which is a struct specific to the llama family of language models in the LLM crate. The path to the language model, and I'll mention this again, but you need to specify the path to the language model file that you download in the .env file. Create that file and add model path, and this is the path to the model that I've downloaded. Change this to whatever it is on your system. We're going to use .env, which is a crate, to load environment variables. So .env, .ok, and then we're going to grab the model path. If it's not set, we need to tell the user to set it. Then we can do load llama, create a path buff struct from the path that we got from the environment variable, specify a tokenizer. I think what this does is just automatically use a tokenizer that was associated with the model that we're loading. I think that's what it does. I don't know exactly how that works, but I seem to get good results with embedded. If we have an error result, we need to panic. There's no point in loading the web server if we couldn't load the model. Okay, so that's that. This is our function for loading the language model, and we only want it to happen on the server side. The reason we can't just use the same feature equals SSR annotation here that we use for the main function is because the result of the function, this llama type here, is specific to the LLM crate. So we actually need to put the use clause prior to the function definition, which means we have to use kind of this slightly uglier syntax instead. So that's why we were doing that. And then now that we have that function, prior to creating the HTTP server, we can just do let model equals web data and then call get language model. So we're gonna wrap the llama model in this web data wrapper provided by Actix. So then when we create the Actix application, we can just do .app data model.clone. And underneath the hood, this app data wrapper actually wraps the data that you give it inside an atomic reference count smart pointer, so it can be shared safely across threads. And by default, ActixWeb, when it starts, it creates, I don't know, 10 threads or something for accepting requests or handling requests. So this one model in memory can be safely shared across all those threads, which is nice. There is something special we need to do in main.rs to get it to serve up the CSS file properly. So we're creating an Actix API simply for serving up the CSS file, and we need to add a service for that. So just paste that in here. So we create this Actix API here, and we add it as a service when we create the app. And so that should help serve up that tailwind CSS. Before I forget, in cargo toml, we want to set this. There's a section we want to add called profile.dev.package.ggml-sys. And I don't know exactly how this works, but long story short, it's kind of an optimization level for the crate that the LLM Rustformers crate uses. And it has something to do with release versus debug build. And I noticed when you don't set this, things are a lot slower. Add this section profile.dev.package.ggml-sys, opt level equals 3. That'll make things significantly faster, at least on my machine. We still need to add .env to the project. Paste it in there. Again, .env is optional because we only want it on the server side. And then we're going to add it to this list. We're going to add it to the list of features in the SSR feature. So dep::env. So now that we've loaded our model and we have this converse API implemented, when we create the send action, all we need to do here is call that converse function. We'll pass in the scope as a first argument, and we'll grab the conversation read signal and pass that to the server side because we need the full conversation context to do that inference. Again, to keep things in perspective here, this is the function that we've implemented in API.rs, and inside that function body, we have all the server-side logic. So everything in here is server-side logic, but we're invoking this function on the client side. And this server macro, this Leptos server macro, is on the client side going to automatically generate code to make an HTTP request pointed to the backend API exposed by ActixWeb, and all that's happening behind the scenes. So we don't actually have to write any code that creates an HTTP request. All we do is invoke this function as if it's implemented locally. The fact that it's an HTTP request to the backend is completely abstracted away from us, which is really cool. We do have to import it, and we're good to go. Oops, this is messages, not message. From this closure, we return the value returned by converse, because converse is an async function, so it returns a future, and create action expects the closure we pass in as a second argument to return a future. So that works out perfectly. So right now we have this send action, and we're assuming that's invoked by our type area component when the user clicks the submit button, which we'll implement later. But all that happens now when the send action is invoked is we add the user's message to the conversation, and we call converse. So we make a request to the server and pass it the entire context of the conversation. So it actually does the inference, but that's going to return. And at this point, nothing's going to happen when the server responds. So action actually wraps 3 different signals that we can use to do stuff when the action is invoked and when the response comes back, when this future is resolved that converse returns. We can write a closure to specify what's going to happen when the server responds. If you're familiar with reactive front-end development, like using React or Solid.js, this is going to be familiar to you, but there's something called an effect, and an effect kind of watches a read signal. We can pass it a closure that will be executed whenever that read signal changes. So there's 2 things that need to happen when this action is invoked. First, we need to add a ... to the conversation when we're waiting for the server to show the user that we're actually waiting on a server response. So if I do what was the last Apollo mission, it's going to put a ... here to indicate that we're waiting on the server. So that's something that needs to happen when the action is kicked off. And then the other thing that we need to do is when the server responds, we actually need to append the inference that was created on the server side to the conversation. So those 2 things need to happen. And so we're going to create an effect for each of those things. We're going to actually leverage 2 of those 3 signals that the action wraps. One is called the input signal, which is a read signal that is modified every time the user basically initiates the action. And in that case, we want to add that ... to the conversation. So we'll do create effect, pass in the context, and then our closure. The input signal in the action is actually an optional or an option. So we need to check to see if it's some. And if it's some, we can start creating that ... message. And this is not from the user, it's from the language model. And then we can leverage the write signal for the conversation to add the ... message to the conversation. So set conversation, update, move, and we pass in a closure that takes 1 parameter, and that parameter gets populated with the current value of the conversation. So we have C will be the existing conversation, and all we need to do is append to it. So c.messages.push and model message. Because we're referencing this signal that's kind of wrapped by the send action, that tells the Leptos framework that this effect needs to run every time that read signal changes. And that read signal is going to change or be written to every time the user kicks off that action. So that's perfect. So every time the action gets kicked off, this closure is going to run. The other effect we need to create is to handle the situation where the server has responded to the client. So we'll create another effect for that. In this closure, we're going to look at the value signal within the send action, and that can some OK response. So if send.value, if it's of the sum variant of the option and then the OK variant of the result, then we're going to execute this code. And when we get a response from the server, see this closure is going to get the value that came from the server. And we already added that ... on behalf of the language model when we sent off the request to the server. So instead of adding a new message, we actually just need to grab the last message of the conversation and change that to whatever the server responded with. So we'll do c.messages.last, a mutable reference to the last one. That's a result, so we'll unwrap it. And we'll change the text to whatever the server responded with. And that should be all we need to do. Not actually handling the case where the user actually submits another message while they're waiting on an existing response from the server. Like the wrong message might get overwritten when the server response comes back. So we're just kind of pretending that case doesn't exist. If you really did want to handle that case, you could handle it one of two ways. One is to just disable the submit button when the user submits a prompt, or you could kind of keep track of which message the server response is associated with. So you'd have to track that somehow with a hash map or something. Again, just to recap, the closure that we pass into this effect is going to automatically be run by the Leptos framework every time the send.value signal, read signal changes. The effect we create here is going to be run every time this send.input read signal within the action is modified. So these two effects are going to give us what we want in terms of updating the conversation when the user both submits a message and when we get a response back from the server. At this point, all we really need to do is implement these two components. So chat area and type area. So we're going to create a new module and we're going to call it app components. Create the directory, and there's going to be two components, chat area and input area or type area. We kind of glossed over this earlier because the app component was already created for us when we made this project from the template. But Leptos has this macro called component, and it basically takes a function. You annotate a function with it, and it creates a component from that function. So we can do chat area. We take the scope and a conversation, a read signal of a conversation as a parameter. And components always return an implementation of into view. And so now, once we have this, if we look back in our app.rs, this is all we have to do to get this to work. So now anywhere we want, we can include this chat area.rs, and in our view template that we return from our component function, we can have a chat area and we can pass it whatever props we want. This conversation right here is shorthand for conversation equals conversation. And we can do that because the parameters taken by the component get translated to attributes on the HTML tag. So let's go ahead and implement this chat area component. Ultimately, it's going to return a view, and we need to pass the context to the view, and then it's going to be a div. In this div, we need to somehow iterate over the entire conversation and output each message and style it depending on whether it came from the language model or from the user. So to put some inline Rust code in the view template, we just surround it with curly braces, and we'll do move this. We can stick a closure in here, and conversation.get, that tells Leptos that we need to re-render this thing every time the conversation read signal changes. We'll grab the conversation, get the messages, and then map over each of the messages, and ultimately output a div containing the message. So in here, this is within the closure that we passed to the map function. We're going to output another view, again, pass it the context. And in this view, we're going to have another div. And in that div, we're going to have the actual string that's wrapped in that message. So now at this point, we have a collection of message strings, and we do need to do a collect into a vector. This allows the compiler to infer what type the Leptos view macro is looking for. Before this is going to work, we do need to make sure this new components module is in the source tree. So we'll add mod components to app.rs. We do need to have some logic for having a different Tailwind CSS class depending on whether this came from the language model or from the user. We're going to make these class strings. These are just lists of Tailwind CSS classes. So this is a list of classes we should apply to the div if the message came from the user. And this is a list of classes that we should apply if the message came from the language model. The language model, it'll make it gray on the left. And if it came from the user, it'll make it blue on the right. Down here in this closure, we need to take a look at the message that got passed in. And if it came from the user, we'll assign the user class to the class string, otherwise assign the model class. And then down here, we can just do on the div that contains the message or the actual text, we can just do class equals curly braces, class stir. We want to automatically scroll this chat area div to the bottom every time a new message is added to the conversation. Leptos exposes something called create node ref, which allows you to get a reference to the actual DOM node. So you can manipulate it like you would in JavaScript. So input ref, create node ref, input, and then the context. We need to do some imports here. Import the conversation model. And then the way we detect when the conversation changes, kind of like we did in app.rs, we're going to create an effect we pass a closure that's automatically executed every time any signals that we reference in that closure are modified. So create effect. And then if the contents of the signal is sum, and the signal that we're going to want to use inside this closure that we pass to the effect is the conversation signal. I don't know if this is the best way to do it, but we can do a conversation.get just to let Leptos know that we care about the conversation read signal, even though we're not actually using the value of the signal. We just want to watch it to see if it changed. And then our effect is to set scroll top. So we're scrolling all the way to the bottom. That's all we're doing. Oops, effect doesn't have 3 Fs. And then while we're in here, I'm gonna paste in some Tailwind CSS stuff for this outer div here. And that should be it for the chat area component. Let's move on to the type area component. This is gonna start out pretty much the same way. We're gonna use a component macro, and it's gonna accept an action, the send action. The overall structure of type area, obviously we're gonna return a view. We're gonna have a div that's gonna contain a form with 2 input fields, a text input and a submit button. So this is the basic structure. Ultimately, what we want to accomplish is when this submit button is pressed, we want to dispatch the send action that got passed in as a parameter, this one right here. We do need to grab a reference to the input field. And then on this form element, we're going to have an onSubmit attribute. And we're just going to implement this inline. This closure that we pass to onSubmit gets past the event that triggered the submission of the form. We're going to do prevent default to prevent the page from reloading. And we're going to grab the contents of the input field. So input_ref.get and panic in the case where we can't get the input field. We can't really do much if that doesn't exist. And then we're going to call send.dispatch, which actually kicks off the action. And we're going to pass it the value that was in the input field. And then, like I said, we're going to clear that input field to get it ready for the next submission. And at this point, all we really need to do is add the Tailwind CSS classes. So I'll do that now. When we create a node reference, we also need to, on the input or on the HTML element that we want that to refer to, we need to put a node ref attribute. So I'll do node ref attribute equals input ref. And I need to do that in chat area too, I believe. So we'll do node ref equals, what do we call it? Chat div ref. So now we've actually connected those HTML elements to the node ref that we created in the beginning of the component. And then this node ref is of type div, not input. The other thing I do need to do is add input.css to the root of the project. I'm just going to copy and paste that in. Hopefully, last thing we need to do, we need to change this style file field in the Leptos section of cargo.toml to point to the output of the Tailwind CSS build process. That's going to be output, and then it's just .css, and then run our Tailwind CSS command. So now we should be able to run cargo leptos watch. Okay, that looks good. So we've loaded the model, it looks like, on the back end. Should I build my web app in JavaScript or Rust? All right, looks like we're in business. Really depends on your specific use case. I'll take it. What about Python? Nice, okay. So we did it. And that is how you build a chatbot using Rust on the front end, Rust on the back end, and only using free and open source language models. And again, this is running on my personal laptop. It's an M1 MacBook Pro, so you don't need some crazy rack mounted server with 4 NVIDIA A100 GPUs in there that costs $100,000. This is just a MacBook Pro. And I imagine this will run just fine on even cheaper hardware. I did cover most of the Rust components of this. I kind of glossed over the Tailwind CSS stuff, and that requires a little bit of setup. If you have questions about that, feel free to ask me in the comments or on the Discord server. I could make a video about that too, if that's something that people want, but there is an example in the Leptos repository of integrating Tailwind into your project. And then also, of course, the code for this project. I'll have a link to that in the description as well. If you do want to take a little break from coding and see a somewhat ridiculous video about next generation keyboards for software development, check out this video where I actually took a look at 7 different keyboards, 1 traditional one and 6 kind of next gen ones, and ultimately choose one of them as my favorite. So check that video out if you're interested. That's it for this video. Hope you got something out of it. Thanks for watching, and we'll see you in the next one.